Ever wondered how scientists create 3D images of the Earth's interior? It's not magic, but it's pretty close. We're diving into a paper that explores the secrets of Teleseismic Traveltime Tomography.
It's like a super-powered ultrasound for the planet, using earthquake waves to map what's deep below.
So it's all about earthquake waves?
Exactly. But it's not as simple as just listening to the echoes. There are a lot of things that can mess with the picture.
Like what? Is it aliens?
Not aliens, haha, but almost as interesting. Things like the Earth's own internal structure, the way we measure the waves, and even the accuracy of where the earthquakes happen.
So let's talk about measuring these waves. The paper mentions two main methods, M1 and M2. What's the difference?
M1 compares travel times between nearby stations, like comparing notes with your neighbor. M2 compares each station's time to the average, kind of like seeing how you stack up against the whole class.
Right, and which one's better?
It depends. M1 gives you sharper details, but M2 is better for seeing the big picture. Think of it like zooming in versus zooming out on a map.
Okay, so the Earth itself can throw a wrench in the works. The paper talks about mantle heterogeneities. What are those?
Basically, the Earth's mantle isn't uniform. It's got all sorts of variations in density and composition, like a marbled cake, you know? These variations affect the waves as they travel, creating distortions in our images.
So it's like trying to see through a stained glass window?
Exactly. The paper shows that these heterogeneities can cause errors of up to half a second in our measurements. That's a lot.
And then there's the spacing between the seismic stations. How does that affect things?
Think of it like taking a photo. If your stations are far apart, you get a blurry picture. Closer stations give you a clearer image, but you need more stations to cover the same area.
I see. So it's a trade-off between detail and coverage?
Precisely. The paper suggests a rule of thumb: the maximum distance between stations should be about 3 times the desired resolution.
Finally, the paper looks at uncertainties in the earthquake locations themselves. Does that matter much?
Surprisingly, not as much as you might think. The relative travel times help to cancel out a lot of these errors. The paper shows that even with significant location uncertainties, the impact on the images is minimal. That's interesting.
The paper suggests a two-step inversion method, combining M1 and M2. Why is that better?
It's like having the best of both worlds. You start with M2 to get the big picture, then use M1 to refine the details. It gives you a more complete and accurate image.
Are there other things that can affect these images besides the 4 factors the paper focuses on?
Absolutely. Things like wave attenuation, the frequency of the waves, and even the accuracy of our measurements all play a role. It's a complex process, yeah.
The paper uses several global mantle models. How accurate are these models?
They're pretty good approximations, but they're not perfect. There's always some uncertainty, and that uncertainty can affect the results. Using more accurate global models in the future will improve the accuracy of the tomography.
The paper mentions artifacts in the images. What are those?
Those are false features in the image, caused by errors in the data or the methods. Mantle heterogeneities are a major source of artifacts.
So what are the practical implications of all this? Why is this research important?
Understanding the Earth's interior is crucial for things like earthquake prediction, resource exploration, and understanding plate tectonics. Improving the accuracy of teleseismic tomography helps us to do all of that better.
What's next in this field? What are some areas for future research?
There's always room for improvement. Researchers are working on better ways to account for the various influencing factors, developing more sophisticated inversion techniques, and incorporating more data. It's an ongoing process.
Let's recap the main conclusions. The paper shows that both M1 and M2 are useful but have different strengths. Mantle heterogeneities are a significant source of error, station spacing affects resolution, and source uncertainties are relatively minor. A two-step inversion method seems to be the best approach.
Exactly. It's a complex problem, but by understanding these influencing factors, we can create more accurate and reliable images of the Earth's interior.
So it's not just about pretty pictures, it's about understanding our planet better. This research is a crucial step in that process.
Absolutely. It's a fascinating field, and there's still so much to learn.
That was a great discussion. Thanks for sharing your expertise.